So we're going to cover a bevy of services in the cloud today. Typically, I would have split this up into 2 lectures and given you half the time to work on the labs associated with each of these services. But because there's no class Monday, I'm going to cover just a bunch of them, and then hopefully on by Monday, you can do the labs that are associated with this. The first one you've been using quite a bit already, so I'm going to just breeze through here. I'm going to point out a couple things that you might want to know about Compute Engine that we haven't covered. And then obviously there are equivalents on both AWS and Azure. Google Compute Engine is Google's version of infrastructure as a service. You're basically renting hardware, and you're creating virtual machines on top of that hardware. This is the lowest level of abstraction in the cloud. And it's what you're used to, right? I have a machine, like a personal computer, and I set it up, and then I give it an address, and then I go and I use it. It's very flexible, but it requires manual management on your end. But it's really good for arbitrary workloads. You can install whatever the heck you want on that VM, and it's all good. You can customize the operating system, customize all the drivers, the packages. For most infrastructure as a service options for all of these platforms, you have this high level of customization on the runtime. So for example, if you're doing machine learning workloads and you need that high-end NVIDIA graphics card, you just configure a VM with all of those hardware requirements that you need. The nice thing about most of these services is that they're billed at a sub-minute level. So you're only getting charged for when the thing is on. So seen previously, whenever you bring up a Compute Engine instance, it does the networking for you. And not only that, it gives you a segmented network where you have a private interface for internal communication amongst nodes in your project, and then a public one for any external facing services. It supports instance templates and groups. So if you wanted to auto-scale your virtual machine, say you put your website on there and you really wanted like the CDN lab to auto-scale it, this is the mechanism for doing that. And it's very similar to platform as a service, as we'll see later on in this class. And then you can set up the load balancing to go across all those services. Okay, the one thing that we haven't covered are these things called preemptible VMs. These are virtual, and I think on AWS, these things are called spot instances. These are virtual machines that you don't mind if you get booted off of. And so in exchange for not minding getting booted, they will give you a huge discount. And so preemptible VMs give you an 80% lower cost solution on Compute Engine. And the reason why Google does this is because if someone has a spike in demand and desperately needs those resources and are willing to pay a premium for it, then they're more than willing to give you a discount when those machines aren't needed in order to be able to charge the higher end person. So that's how they're making this actually make money. This is why the service class exists. And 80% is a good price point that makes them a lot of money, apparently. It happens, well, so it depends on how you use the thing. So the usage cost on a VM does cycle. So if you are trying to, like these folks, Framestore, this is a video rendering service. So this is like YouTube. You upload a video to YouTube, it's sitting there transcoding the heck out of your video into all the different formats. That's a lot of compute cycles. And so if you have a service like that and you're spinning up a bunch of cores, you don't want to pay full price if you don't have to. And so with the 80% thing, maybe it's a batch job. Maybe, I just need the result in maybe like a day. Or like if you're rendering a Pixar movie. Well, I think Pixar has their own cluster. But if you're doing something like rendering a Pixar movie and you're like, oh, you know what? I'll let that go for a day. And then maybe for an hour, a spike of demand in one website would cause all of your VMs to terminate. Then you would just wait for that spike to abate and then just restart the VMs. So that's much cheaper, and it would only delay you for the time that there is a spike. I think Azure had this outage on the East Coast like last week where they ran out of VMs in the eastern region. So they obviously haven't over-provisioned enough to handle that spike that would allow you to do this. Okay, so this is just an example. I pulled this out of a podcast, a Google podcast. They need 15,000 cores, and if they're paying full price on 15,000 cores, that will take their bill way up. So if you can get an 80% discount, why wouldn't you? So this is a facility. If you end up in a company that's got this enormous compute job, you would look at doing this. The drawback is that you have to make your application fault tolerant, right? Like if a job goes down and you are preempted, you have to have logic around there that will restart that thing, resume that thing after you can. So they have this case study. They're basically saving hundreds of thousands of dollars by doing preemptible VMs. And all they have to do is build into the application to restart interrupted jobs in order to bring it back up. So I just wanted you to see that, because this isn't really, we don't have a lab that does this. The other thing I want to cover is ways of accessing Compute Engine. I briefly talked about this before, how that you can do it through the web console, which is the UI. You can do things through the command line interface with the gcloud command. You can do this within Python code or JavaScript code or whatever your programming language code is. And this is access to the Compute Engine backend. So your ability to start and stop resources can be done via a programming language code. The other thing you can do is to use the REST API directly. And in fact, the whole thing is fronted by a REST API. So these are really 4 different ways for you to control all of your resources on Compute Engine. In fact, these 4 ways will work on any resource on the back end of Google Cloud. So however you want to programmatically manage your cloud resources, you have all of these options available to you. So here's the example you've been using so far. This is the web UI that you're all hopefully really familiar with. The command line interface for Compute Engine is gcloud compute instances list. So this is used in a couple of places where you're just in Cloud Shell, or you have the SDK installed on a Linux machine, and you set your project ID, set your credential, do a login to get your credentials, and then you can from the command line access all of your things. And so there's this hierarchical command set up with a gcloud interface. This all tab completes. So if you don't know what commands to use, this all will tab complete to tell you what different things are available to you. So creating, deleting, and that sort of there's a whole library of these commands that you can do from the command line. The other way is via libraries and the API. We'll talk about the libraries first. So if you go into the developers region for Google Cloud, you'll see that there's development environment SDKs for a whole bunch of languages. So of course we're doing Python. So the Pythonic way of getting the libraries to communicate with Google Cloud. In this case, there's this Google API Python client package. There's actually multiple Python packages to do this. This is just an example using this particular package. And then what this does is if you say, hey, build me, so this thing is actually going to build you a Python package dynamically from the REST API specification. So this is really good, because what this does is that it keeps up to date with the REST API. So if somebody changes the REST API, I can basically do this and get those changes into my Python package without actually having to do a pip install. So that's just trivia that you may or may not come across. So one of the things you could do is if I import this and I build the API package called compute, then I can just do compute instances list. This is my project name, the zone I'm looking at, and then just execute that, and I'll get the return just like I would on a gcloud compute instances list. So Python example. And then the other one is via the REST API. If you go to your web UI, and then you go to API services, library, and there's a list of all the different APIs on Google Cloud. You can click on something, for example, I want to show you how to use the Compute Engine REST API. There's this button over here that says try this API. And what it'll do is it'll give you a web interface that will show you the REST endpoint and the syntax of the REST endpoint, which is this. And you look, it's like, hey, this is exactly what a REST API should look like. You do a get to list. and then you're listing the compute instances in this project in this zone. And then what you can do is you can send that API, the different project in the zones, and it will fill in this request interactively. And so you basically send an HTTP request directly to this API as a fourth way of navigating in the cloud programmatically. So here's an example. If I do something like this, I do the REST API call as a HTTP request, and then I'll get a JSON response that gives me all of the results from that API Explorer. Okay. Are there any questions about this? We'll do a lot more with the REST API stuff when we get in a couple of weeks, when we're looking at more of the machine learning APIs, because all the machine learning APIs can also be tested out doing this kind of mechanism. Okay, the next thing I want to talk about is storage as a service. And to give you a background of this, I'm going to go back to 2003, right when Google was really starting to take off. They had this problem where the amount of content on the internet was exploding, and they didn't have a file system that could support all of that. So the search engine is sitting there downloading all the content from the internet and processing it, indexing it, building all these different indices based on search terms. And their file system, they needed an enormous distributed file system that was fault tolerant. And if you start deploying clusters and clusters of CPUs with disks in them, the disks have a mean time to failure of like 10,000 hours. But if you have 10,000 disks, you're sitting there replacing one every single hour, right? You need a file system that when the disk fails, you can automatically patch that. It'll automatically heal the failure. And then you need it, also, if you add a bunch of disks to it, it needs to automatically increase the capacity and then load distribute the current content into the new resources. So all of these problems led to the design of the Google file system. And so they had large data sets, they needed high throughput, low latency, they needed durability and availability, and they needed this with very little management overhead. And the design of this is in this paper, this SOSP paper from a long time ago, and they're using a lot of the same techniques that we'll see being used in the databases, in the scalable databases. They're using horizontal scaling, they're using replication, they're using adaptation to shift the data and the replicas to wherever it's being used. Okay, so initially this was all proprietary, and then Yahoo reversed engineered what was being done, and they released the open version of this as the Hadoop distributed file system. And then this is now managed by Apache. So if you want to in-house this kind of technology, then you would go and do this HDFS implementation if you had an on-premises thing that you wanted the storage capacity and the management of Google. So Google took this and then spun this out commercially into what you use right now is Google Cloud Storage. AWS has something equivalent in S3. And what this is a fully managed no-op storage service. So it's serverless. You don't have to go to a particular server to get your data. You just give it a URI, and that URI doesn't specify a server like an HTTP URL does. The URL in a website, you're actually pointing at a server. The URI for Google Cloud Storage is just a name. It's just a key. And the underlying serverless backend is mapping that to the actual replicas that are implementing that bucket is effectively what it is. And then it automatically backs up and versions everything that's there. There's no management costs on the client end. Okay. The other thing that it does is that it automatically replicates and then caches the copies over multiple zones and regions. So if you're trying to serve a static website from your cloud storage, and all of a sudden it gets really popular throughout the world, then what GCS will do is it'll automatically, if you set the bucket to be a multi-region bucket, then it will automatically push cached copies all throughout the global network where the demand is. And this is where decoupling that URI, like when you do a gs:// and it's some bucket name, that thing could actually be existing everywhere. It's sort of like 1.1.1.1, right? You just get to the closest version of that can handle that request, and you'll deliver the data. If you know that you're going to use this bucket for local computation, so say you have a high-performance cluster that's in US West 1, and you know all the computation is going to be in the DAOs. So I don't want any of my data anywhere else other than the DAOs. You can specify a fixed region. And then this is typically cheaper when you say, hey, this bucket should always be local. Okay. And that is a typo. Fix that. Okay. So this thing is massive. You can get buckets in the orders of hundreds of terabytes to a petabyte. And it just scales up. Okay, so the model of usage is done the same way that AWS does their S3 buckets. So the abstraction is a bucket. They're just like URLs. They must be uniquely identifiable, but they don't map to a particular server, is the idea. The other thing is that this is object-level storage. It's just like a web server. I'm going to go and retrieve objects in their entirety by some kind of handle. This is different than a Unix block storage system where you can just randomly access different bytes of a file. This is actually, you get the whole thing. You give me a handle and I give you the whole file back. There's no other way of accessing the data. Okay, so when would you use cloud storage versus something else? It's basically used for large unstructured data that doesn't need to be queried. Yes?
Wait, I think I lost the bucket. So is the bucket like the file in the Google file system? Or what is the bucket again?
A bucket is a collection of files. So this is your abstraction. It's your handle. It's the unique identifier that organizes all of the objects that you might put in it. You can have multiple buckets, and these all have to be unique because it's implemented by Google Cloud Storage. So those are uniquely identifying the data to the project that is using it. Yeah. Okay, so this is good for unstructured data. So images, videos, zip files. If you have structured data that needs to eventually be queried, then you need a real database. Now you could try and fake it out. Like you could actually do some querying, like it's sort of like a massive grep in the file system. I can do search. I just do grep on my 10 terabytes of disk data on Linux. But if you're going to do that kind of operation, if you're going to do that operation a lot, then what you would really need is a database. So the stuff in Google Cloud Storage is typically not stuff that you want to query. For that, we're going to do something else. Okay. It's often used to feed or store data to some of these other applications. So for example, if you have a large data set that you eventually want to query, you might store the raw file in cloud storage and then import it from cloud storage into BigQuery, which will then build tables that you can query out of it. So it'll be a source or a sink for other services in the cloud platform. So we'll show you some examples of each one of these. In fact, you do some of these in your lab. Okay, so just like the compute engine, you could use a web interface, you could use the SDK, and the command for that is gsutil. You can do it from Python, and so here's another way of including Python. If you import from Google Cloud, you can instantiate a storage client, and then you can actually access the client programmatically in Python. And then again, it also has a REST API that you can actually try online, so you can see the kinds of requests and their formats to get the API calls through. And any of these in your project are fine. Okay, so we talked about structured queries. This leads us to database as a service in the cloud. So the main types of databases in the cloud are either the SQL databases or the NoSQL database. We covered this earlier, where SQL is the relational structured data. It's got all sorts of support for querying, and it's got this strict schema that you have to adhere to for your data, whereas NoSQL, non-relational, unstructured, and it's got very simple queries. Simple key lookup queries is all that it really supports. But you can scale this really well. So with regular SQL, most SQL databases implement strict transactional consistency, and if they need to scale, because they have to support this consistency model, they can only scale vertically. They can only add more iron to a single system to scale up requests. Whereas in NoSQL, you have this loose eventual consistency, so this allows you to do a distributed database really a lot easier, because you don't have to worry about synchronizing and consistency as much. Okay, so what is driving the fact that this gives you one class of consistency and scaling and this gives you another? Well, back in the early 2000s, there was this CAP theorem that was proposed. And the CAP theorem goes like this. It says any network system can have, at most, 2 of 3 desirable properties. It is impossible for you to do all 3 of these things. So the first one is consistency, strong consistency. So if you really care about that, that could be one of your 2. The other thing is high availability. So if you want the thing to always respond to requests, that would be what availability is. And then the last one is the ability to tolerate partitions. So you can do 2 of the 3. You cannot have strong consistency in the wake of network outages with high availability. And this is the theorem. So this leads you to 2 consistency options for network databases. The one that SQL databases take is the ACID property, strong consistency. And in order to achieve strong consistency in the face of a network partition, say you tried to shard your SQL database amongst multiple versions, in order to get strong consistency, when these things are partitioned, you can't do any more writing into the database, because all the replicas really need to see the transaction as it's being committed, otherwise they'll get out of sync. So this is the ACID property that kills availability whenever there's a network partition. And this is what Cloud SQL will do. If you start sharding Cloud SQL, and then you have a partition between the replicas, this thing will stop being able to write transactions. The other one is base. This is basically available soft state eventual consistency. And then here, if you want high availability in a network partition, you lose the consistency. And this is what Cloud Bigtable and Cloud Data Store, a lot of these NoSQL databases are doing. You will tolerate the fact that not everyone sees the same version of your data at the same time, just to get the scalability and availability in the face of a network partition. Okay? Yes?
For the ACID thing, so you can still write to those, right? But is it just like a higher latency because you have to wait for like to hear back?
To reconnect. They will not commit that thing. So if you have a transactional thing where if you have multiple transactions that have to be atomically committed, that thing won't go through until the replicas are reconnected.
Oh, so this is like assuming a replica's down.
Yes, like you have some partition in the replicas, yeah. And you would want this, so if you have a large distributed database that's got multiple replicas across the world, you want them to be consistent. If consistency is your #1 goal, then yeah, you would have to pause operations if the replicas can't agree online what the legitimate version of your database is. And so we cover this in the blockchain class, and I'll talk a little bit about blockchains. Blockchains do something kind of similar here when nodes of the blockchain can't connect with each other. They have to figure out, what is the actual version that I'm going to commit to is the idea. Okay, so your application that you're building needs to drive the consistency model. And you can think about your application and say, oh, I can do with base, or I can't do with base, and I have to go with something like an ACID model. So if you are managing bank accounts, that thing probably needs strong consistency. So if your business depends on that, then yeah, okay. Then I need the ACID thing. And it's no surprise that the very, very first sets of databases were these ACID databases, because a lot of the banks were using SQL databases for all of their account information. But if you have a game and you have the high score updates, you have a top 10 leaderboard, well, you don't need strong consistency on that. You need eventual consistency, right? So if it just takes a little longer for that high scoring score to get committed so that everyone sees it, you're okay with that. Okay? So the fact that there are these diverse kinds of data requirements, this leads you to the alphabet soup of data backends in the cloud. Like when you bring up AWS, you see like maybe a dozen different types of data storage services. And so I'm going to just briefly talk about some of the kinds that are out there, but really this is the reason why you would have custom data backends for a custom application based on what you need. Okay. The other thing I want to talk about are the architectural options for implementing database backends. The first are the server-based ones where you're actually managing and deploying the machines. And then these machines would be pre-configured with whatever database you need to have running. So examples of this are Cloud SQL, which you've run already, and AWS RDS. These are versions of popular databases that you would just bring up like a virtual machine. It basically, what it does is it automates away the installation of the software and a little bit of the configuration, but in the end, it's basically a virtual machine running some piece of database software on it. The other kinds are the serverless kinds. And these are just completely, fully managed, no-ops database services. This is like Google Cloud Storage, but applied to your database, right? Like I have some mythical database, and I'm just going to write to it, and then I'm going to query from it. I don't need its IP address at all. In fact, it's not even given to me. There are no IP addresses in this model. And so some examples of this, the one that you'll be using is Cloud Data Store for your project. But AWS has this DynamoDB, which is similar, and then there's also Cloud Spanner, which I'll talk about. Okay, so serverless applied to databases. So what does this look like? Well, if you are running a database on-prem, you have to do all of this, right? Power, rack, server maintenance, operating system maintenance, database software maintenance, and then your app can connect up to all of that. And then you also have to worry about scaling. If that thing, if you need extra replicas, then you also have to do all of that. So this is what we have right now. The application provider is having to do all of this. When you go to IaaS, then what you're doing is you're getting rid of this part. And you're having the cloud provider sort of do that for you. If you go to a server-based data store, you're basically getting rid of this. I don't have a picture of it, that's why I'm not here. But then this would be sort of light green, and then you would be forced to do that for MySQL. So Cloud SQL, RDS, if you needed replicas and scaling, you would have to manually configure that in your project. The serverless ones, and what I call database as a server, you basically have your app, and your app writes directly to some mythical backend, some abstract backend database. And then you're interfacing that way, and then the cloud provider is doing all of this. Just like the cloud provider does all of this for a storage bucket. And all you're doing is getting stuff from a URI. Okay. Is that clear, the model of serverless databases? Okay, so we'll first just run right through server-based databases because you've already done these labs. So Cloud SQL, RDS, and Azure SQL, which is an MS SQL service. So these are just drop-in replacements. So if you have a legacy app, and that legacy app would take you years of engineering to go serverless, then your move to the cloud is to just get one of these RDS or Cloud SQL instances up and then just migrate. Just do an export of the table data and do an import on the other side. Point your application to the new replica in the cloud, and then that's it. That's all you would want to do. Because it does take some re-engineering to shift what you're doing right now on premises over to something that's serverless. And that's what these things do. They have pre-configured virtual machines that will scale the size vertically on demand if you feel like you need more resources. And they're all accessed via standard drivers. You don't have to change the software on your application to get it to work with any of these backends. But we're interested in serverless databases now. So what are these? The first one we're going to talk about is Cloud Data Store. This is a NoSQL database. And the equivalents on AWS and Azure are these two things. So what is this? It's distributed, fully managed NoSQL database. And it's optimized for reading. It's not really good for a bunch of writes. It's schemaless key value stores, so just like a Python dictionary, you can have a key and then any of the data types could be the storage. There's no schema. It has very limited querying. So it's mostly gets and puts to this backend. So this is a trade-off, right? If you want scalability and performance, then you're gonna trade off the ability to query fast. Okay. It's all serverless operation. Cloud Data Store figures out your usage pattern and will automatically do the replicas of your keys and data on their backend as it's needed. Okay. The way you access Cloud Data Store, you can do this. There is a REST API, but typically you would do this from within your app using SDK, like Python SDKs. Okay. So for Cloud Data Store, this is the model, and I'm going into the details of Cloud Data Store because this is what your backend is going to be for homework number 4. But the details, these details are very similar for whatever NoSQL backend. So this is the terminology that is used in Cloud Data Store. The data store, in Data Store, the data is organized by this thing called a kind, and you can think of kind as the table name in SQL. And this is a way of just organizing your data store backend because that data store backend is shared amongst everything in your project. Like when anything in your project wants to do Cloud Data Store storage, it goes to the same Cloud Data Store instance in your project. And so if you have separate parts of your project needing different tables in the Cloud Data Store database, you would specify different kinds in order to keep the data organized. And so you'll be doing this in your lab. I will show you a way of doing the guest book where the kind is like a review. But then you're going to need to create a different kind for your bubble tea app. And you'll create, I don't know, whatever table you would like. But that will keep the guest book data different from your bubble tea data. And you'll need that in order for your app to work. Definitely don't use the same kind for like, in fact, I think in the lab I have you delete. I think I have you delete stuff just to make sure you're not using the same kind. So here's an example. I have a data store backend that has this book as sort of the table. And then within this, I have an entity, and each entity has the key, and then the key has some kind of blob, which are the properties, and then this is your value store. Okay. So each entity has to have a unique key for the kind that it is associated with. And these keys are basically like rows in this table, each one of these keys. And then these are like the columns of a database where they have different column names. But note that when you insert this row, in NoSQL, they could be different. Like the actual fields in these things could be different because it's NoSQL. Okay. So some of the operations, you can do the insertion and retrieving via puts and gets. You can do minimal queries with the query, the scan, and the fetch. And something like scan will go through the entire database and give you all the entries back, which is actually okay for your bubble tea app because I'm having you dump all the stores in your backend. So you could do a scan or a query to get all of those entries back. And so this is where the model comes in. You have an abstract model that does a select, that does an insert, and then maybe does a delete. And for your SQLite 3, you were doing selects, and you were doing insert intos. And for Cloud Data Store, you've got the same interface, but on the back end, in your model _ data store, you're going to be doing puts and gets and scans. And because you have hopefully architected the thing modularly, it should be one drop-in file to implement model data store, and it should just move over to a serverless implementation. Yeah.
So with these serverless systems, is it like the fact that the cloud provider is configuring everything? Is that what is limiting your ability to like query or do like complex?
It's also the architecture of NoSQL that's allowing you to do this. And in fact, I will show you Cloud Spanner is meant to be this horizontally scalable ACID database. So you get the best of both worlds. You can get the performance and the querying. So that'll be the next thing. So different backends will implement things differently based on your requirements. So for Cloud Data Store, they're like, oh, we don't care about querying. We just care about simple gets and puts, which is most web applications are just doing simple, like a user profile. Let's just fetch that user's profile from Cloud Data Store. I'm not doing a huge query across all of the users in my backend to do some operation on the website. So then this makes sense for a game application, for example.
Are you able to control like how the data is sort of nested, just like depending on like what type of queries you might want to do, or is that like
you can, yeah. So in DynamoDB and in Cloud Data Store, you can specify other keys to build indices off of. If you really want to try and do a little bit more for the querying than what's there, there are secondary indexes and secondary keys and sort keys in DynamoDB that will allow you some limited querying support, but it's not intended, it's not really natural to implement this full-on querying on a NoSQL backend done this way, yeah. It's for pretty simple, but maybe large-scale data is Cloud Data Store. And so if you actually are trying to pick a backend for your application, these are things that you would want to think about upfront, right? Like, what is the common use case of my application? And then you would find the cheapest service that would give you what your application needs to store your data. Okay, so here's some summary. You want cloud storage on this end. If you have large data that doesn't need to be queried, maybe you would do some of these NoSQL databases, but if you do really need a bunch of querying, maybe you're over there on the Cloud SQL end. Okay. And so with that, I'm going to briefly talk about some of these other data stores. I'll just run through these things quickly because we're not going to use these things, but you should just know the different flavors of databases that you might run into. One is Cloud Spanner, and I think Amazon Aurora's is something that's similar. And this is known as NewSQL, is what they call it, because they didn't like NoSQL. So NewSQL, well, Cloud Spanner is this horizontally scalable relational ACID database. So it's trying to do the strong consistency and support SQL, but then allow you a whole bunch of replicas. And it will try and keep those replicas strongly consistent. So it wants to give you the best of SQL, all of the queries, and the querying support, but then give you the best of NoSQL, which is this horizontal scaling. So this is their goal. And so we just talked about the CAP theorem. What is Spanner going to do? So Spanner does something kind of novel. It basically wants to keep consistency at all costs. But what it's going to do is it's going to punt slightly on availability whenever there's a partition. And hopefully the partition is going to be short-lived. And so Google made this observation that its network very rarely goes down. And so if they can optimize the protocol so that in the rare case there is a partition, you can still do a bunch of reads. And whenever you do writes, the writes are committed as long as you're within a partition that's got the majority of nodes. So that's the idea. That's the difference. So rather than freeze everybody's availability when there's a partition, what it does is it figures out if you have a quorum, it'll allow you to continue. And then when the network reconnects, the quorum's data is the definitive one, and that gets copied over. So that's basically, in a nutshell, that's what Cloud Spanner is. Yeah. You have to invalidate. So say you have the majority partition and the minority, if it knows it can't connect up to the other replicas, it is not allowed to accept writes because it knows it's not part of the majority. But if you have a quorum, so say I have 3 Spanner nodes, and this is the default configuration. This is what cost people, like when I used to do the Spanner lab, by default, it brings up 3 N1 servers. And in a partition, you're either with the 2 or you're with the 1. If you're with the 1 and you can't connect up to the other 2, you would not accept any writes. You could still do some reads, but you're not allowed to do any writes because you're not part of the quorum, whereas if you are connected to the 2 in the majority, you can make progress. So that's the tweak that Cloud Spanner is trying to do. Did that answer your question, or? Okay. So this is good for online transaction processing, which is, if you do care about the consistency of your data, you want a definitive copy at all times. This is the kind of stuff you would use. And of course, there are a bunch of services that need this. They don't want to do sharded Cloud SQL because that has its own management issues. So they are willing to go with a serverless SQL. This is effectively what it is, because really the 3 replicas are hidden from you as a user. So you don't get to actually see. You can you're not intending to see what the IP addresses of the servers are. They are sitting there running in your project, but you would never access it by IP address. You would be accessing it as if it were serverless, and then it's doing all the management for you. And this is really powerful because these folks, so Unity is doing this. It's using Spanner, and Unity's this game company that's implementing a worldwide gaming network. And so they would use something like this that before they would use sharded SQL, where they would do replicas and then try and run a consistency protocol amongst the replicas. They're like, forget that. That's not my core competency. I hate SQL. Can I just use this serverless SQL that does this stuff for me? And so this is why they moved over to something like this. Okay, so this is an article if you want to see exactly what the motivations are for people that are doing this. So another example is blockchain.com. So if you know the blockchain, it's an enormous sequential log of transactions, and you actually want to query that thing. You don't want to have to replay from transaction 0 all the way to transaction 5 million to build some kind of querying thing around it. And so what blockchain.com does, this is a site that allows you to do arbitrary querying of the blockchain data. And it's using MySQL to import all of this data into it and then create the tables of common queries that people might have onto the back-end blockchain. So that's another implementation. Okay. So that's all I'm going to talk about for Spanner. You'll find that there are other data store types that are available in the cloud. One other type is this thing called Cloud Memory Store. And so the application use is for something like an online profile for a bunch of gamers. This thing is read very frequently, as, for example, if you go and you look for the leaderboard, or if you're trying to look up people, you're going to read these entries very frequently, but then the updates are very infrequent. If you have this operation where it's read all the time, but very rarely updated, this is a good candidate for caching and replication. And in fact, when we talked about the load balancing and how you wanted to keep the cookies in order to avoid the cookies and the SSL state, so to avoid the handshake, I showed you a picture of Elasticache, which is this in-memory data store. That's basically what this is, Cloud Memory Store. So some other names, Redis is the sort of the open source version of this. And what it does is takes simple key value data and it tries to load all of it into memory. Because memory accesses are fast. They're expensive, but they're fast. But if you have a cluster of a dozen machines and you're using all of their memories to store some of this stuff for fast lookup, that can give you an acceleration for your application. So these are application accelerators typically, these in-memory data stores. So Cloud Memory Store and AWS Elasticache, these are hosted versions of Redis and Memcached for speeding up lookups in the cloud. Another interesting system is called Apache Kafka. So what is Kafka? Kafka is a log-based data store. So the idea here is it's similar to Git. You have a base file, and then all you're doing is storing deltas. And then in order to get the current state, all you do is start from the beginning and replay all the changes. So you can think of that as being a way of actually implementing an entire file system. And this would get rid of ransomware, right? Like, if this is how I store files in my backend, and all of a sudden that last change was to encrypt everything else, Well, then I can just roll back to the previous version. So you can think of Kafka like that. So it's basically a versioned file system, and the way it versions it is to put everything in a log file, all the changes into a log file. The example use case, this is an article that's a really interesting application of Kafka to the New York Times. So the New York Times has 161 years of published content. It requires in its site for you to be able to search based on topics. It requires that the latest version of content always show up immediately when published. So if you have an article and the article has changes, the reporter has changed different details of the article, you require that to be versioned. You want to do some personalization. So on a news feed, the user wants different kinds of articles. You want to be able to access all of this content to support all of these different applications of the consumers. So this is the producer, this is all the consumption, and you want to be able to support this efficiently. And so this is a figure of what they had before they went to Kafka. They had a bunch of content management systems, and these were all running something different, right? Like here might be some of the photos, here might be some of the articles, and they were all running their own CMS using disparate schemas, disparate software. And all of these things exported a REST API. And then the consumers, the search, the personalization, the collections, all of these things would be basically bombing the REST APIs to get what they needed, and then consuming those things to deliver the actual content on the back end. Okay, so this was not scaling for them. The engineering costs of managing all of these APIs, all of these different systems, and then for these things to keep up to date with what's going on, this ended up being a huge cost investment for the New York Times. So they moved from this model to this model. And so in this case, you have these basically decentralized logs. And so all of these content management systems would publish all of their things to topic queues. So that's what these things are in the middle. And so maybe all the sports, this might be like all the sports articles. They would get different articles, maybe football, soccer, and then split by teams. So you would publish that into this this basically sequential log, and then all of your consumers, the way it would build their data products would be to just ingest the log. And then ingest the log on the topic that you really care the most about. And this allowed them to, because this is almost like a uniform, you can think this is the narrow waistline of the data layer for the New York Times. They can standardize on this, and then they can build on either side of this. They add a bunch of CMSs, and then that goes into this interchange format, basically. And then all the different products that they're producing will just consume these logs as their interchange. And this ended up saving them a bunch of engineering and resource costs as well. So that link in the previous one is a good one to read if you care about log-based databases. This leads you to blockchains, which is also a log-based database. Blockchains are these append-only databases, and because I'm teaching the blockchain class this quarter, I'm going to skip this, but if you care about blockchains, you can take the blockchain course. So I'm going to skip this. I used to go over this when I didn't offer that course, but I'm not going to anymore. The last type of data backend is the data warehouse. And this is something I'm going to cover in the last week of class, but I wanted to show you this right now as a preview. So if you are an application like a website, and you are generating all kinds of access log information on your site, and you're storing them in some enormous backend, you want to be able to have a way of cheaply being able to query all of that monolithic data. So this is where big data comes in. I have a massive data set, and I want to support limited querying in a very efficient way. And so this is what a data lake or data warehouse will do. And the examples that we'll be using at the very end of this course are BigQuery for your labs. I just wanted to preview that for you. This is all done serverless. Right? You don't have to set any of this stuff up. You just publish all of your data to BigQuery, import it, and then it will spin up all the resources you need to do particular queries on its backend. Okay. And so with that, I'm going to take a 5-minute break, unless there are questions. Okay, so we'll break then.